Good day, Math 30-1s. Thank you for joining me in a conversation about some released items from 2019. We are going to be looking at 28 multiple choice questions and 8 numerical response questions, essentially a full machine scored section of the diploma, and we're going to be looking at these over the next little bit. And one of the best things that you can do is attempt each question before we go through it together and hear some strategies, but feel free to pause the video, test some things out, and listen to some logic as well. So let's begin looking at the released items from Math 30-1. As I said, we are going to be looking at a full-length diploma here, so feel free to get comfortable and get a piece of paper, pencil, and pause as we go along. Our first question here tells us that there is a point P, 3, 8, and it's on the graph of y equals b to the power of x. And b is greater than 1, so this is an increasing function. The corresponding point P prime is on the graph of, and there's another one listed here. Now, we know a little bit of information about this graph, but it's asking for a bit of information about a different graph. And often on the diploma, what it's looking to do is it's looking to try to connect these two graphs with some information. But the problem with our new graph is that we're missing a b value. So how do we get that b value? Well, we do have a little bit of information about that first graph. So what we're going to do is take this y equals b to the power of x and plug in the information that we know. There is a point. When the x value is 3, the y value is 8. So what we're going to do is swap in some information, plug it in, and see if we can figure out what b is. Now this is, again, great opportunity. If you haven't paused yet, pause it, try to figure a few things out. But you might logically say something cubed is 8. And you might know right away that the b value is 2. You can also try to get this to a common base. 2 to the power of 3 is b to the power of 3. And again, if the exponents match, so 2 should the bases. You can also cube root both sides. And so if you cube root both sides, you do end up with a b value of 2. So however you get that, b is 2. We then have this other information where we're told that y plus 3 is b to the power of x plus 1. And I'm going to swap out that b with a 2 because we know that information now. And this question really is asking about the corresponding point p prime. Now we do know that this graph has either an input of 2 or an input of 4, and so luckily we only have 2 things to test. So I'm going to subtract this 3 over to the other side and basically make this a y by itself. So I might just test this 2 value as an x to see if an 11 or a 5 comes out and just see what happens. So let's plug in that x value of 2. 2 plus 1 is a 3. I'll do this a little bit more concisely and see if a 5 or an 11 come out, because that's essentially what we're looking for. Now, 2 cubed is a 8 minus 3, and a 5 does in fact come out. So when a 2 was plugged in, a 5 in fact comes out. And we're looking for that as one of our choices. Conveniently, B is that choice. You could very well plug in a 4 and see what comes out, but ultimately I'm feeling confident with 2, 5. This next question, again, has this information box at the beginning, and there's some rows that indicate a domain and range that are supposed to be the response or the choice. So this one says the function y is equal to f of x has a domain of the set of values x such that x is greater than or equal to but less than or equal to 6, and x is an element of the reals. And there is a range of the set of values y such that y is less than or equal to -4 and less than or equal to 8, greater than or equal to -4 and less than or equal to 8, and y is an element of the reals. And there's a transformation that it undergoes where I'm noticing a vertical reflection or a vertical flip about the x-axis, and I am noticing a horizontal stretch by a factor of 2, remembering that the input has that reverse effect. So if we do see a b value of 1/2, the effect is actually horizontally being stretched by 2. So I'm looking at this domain between 2 and 6, and I'm looking at these y values between -4 and 8, and I'm trying to apply these transformations to determine the new domain and range of the transformed function. Which row does this get indicated? So one of the best ways that I like to do this is to visualize the domain and the range and see how these transformations impact that. Now I'll start with the domain and just see if this gives us a little bit of help. I know that this is initially between a 2 and a 6, and I don't really know what's happening between the 2 and the 6, but there is some sort of transformation being applied to this function that's between 2 and a 6. So I'm going to try to just change the color here so we can visualize the actual impact. And it does say there's a horizontal stretch by a factor of 2. So what would that do to the 2 and the 6? Well, they would stretch that 2 out to a 4, and it should stretch that 6 out to a 12. So now something is happening. I don't know what's happening, but something's happening now between 4 and 12. And I'm looking for a domain option that is between a 4 and a 12. So what is happening between a 4 and a 12? Looking for one of the options between a 4 and a 12. Not negative. There's no flipping that's happening. Nope. The only option should be a D. And it's always good to verify this with the Y values to make sure we're not misled in any direction and that this is all kind of validated both directions here. So if we look instead at the vertical impacts, we are starting off between a -4 and a +8. Now this is not to scale at all, but something is happening vertically between a -4 and an 8. And the impact is a vertical flip. So let's see what happens in a vertical flip. That -4 flips up to a +4, and the 8 should flip down to a -8. So we should see some new values here, and that 8 should go down to a -8. That 4 pops up to the -4 pops up to a +4. So we should be looking for values between -8 and 4. And I am, again, feeling confirmed with that option D between a -8 and a 4. And there was some choices here, -8 and a 4. This is maybe is trying to get people to not do anything. But ultimately, I'm feeling confident with that option 2. Okay. Again, pausing these is a great way to, again, test your logic before we jump into some conversation here. So this next question, multiple choice 3, says the graph of y equals f of x is transformed onto the graph of y equals g of x. I'm noticing there's an f of x and there's a g of x that are labeled in this graph. And it says an equation for g of x in terms of f of x. And I'm noticing that the graph for the function g is created based on some transformation from f. So I'm looking at the graph f and I'm saying, all right, how do we take this f graph and make the g? So let's consider some of the options in the multiple choice. I'm seeing there's a vertical stretch by a factor of 2. I'm seeing a vertical shift by a factor of 10, so moving up 10. And I'm curious about that shifting up of 10 because I'm seeing a lot of these values on this x-axis being locked in there. And then I'm seeing some horizontal impacts. Is there a horizontal stretch by a factor of 2 or 1/2, and what's actually happening? So as I look at this graph now, I'm thinking about, well, what's actually happening vertically and horizontally, and what is creating this new function g? So as I look at the function g, I'm noticing there is initially a distance of 1, 2, 3, 4. There's a distance of 4 there, but for the function g, we'll just change the color here. We're seeing 1, 2, 3, 4, 5, 6, 7, 8. So from a 4 to an 8. And I know this scale isn't 1, 2, 3. It's actually by 5s, but I'm just counting the grids for this to say it's looking like it's twice as wide. So it looks like it's being stretched horizontally by a factor of 2. So if it's a horizontal stretch by a factor of 2, that would imply the b value should be a 1/2. So I'm looking for a b value that's a 1/2, leaving us either with a choice B or a choice D. Good. We're getting a little bit closer. Now with this, we then have to think about, okay, well, what's happening vertically? Is this shifting up? Is it stretching up? what's actually happening here. One of the things that I do notice from the x value, from the y values, y is 0, at these two endpoints here. If there was a vertical shift, we would see this function g moving up, plus 10, and that would be shifting up 2 grid lines here. But I'm not seeing that vertical shift. I am noticing that a vertical stretch about the x-axis here, this vertical stretch times 2, as I look at these options in here, a vertical stretch times 2. If the y value is 0, stretching times 0 doesn't really stretch anywhere. So it kind of makes sense that those 2 points on the x-axis were locked in, because if y is 0, timesing it by any number doesn't really move it anywhere. So I'm noticing that this is probably going to be a vertical stretch by a factor of, now again, this is at a 10, it stretches up to a 20, so I'm noticing this is stretching up times 2. So I'm looking for one of my options to be vertically stretching by 2, and I am again noticing this option D. All right, on to number 4. Again, have a look. Feel free to pause at any point. But if a point A at -3, 4 is a point on the graph of y equals f of x, then the corresponding image point A prime on the graph of y equals 1/2 f of 3x plus 12 minus 1 is located where? So this is asking for this point to undergo some transformations. And you might just look at this and say, well, what's happening to x? And move this x point along the way. You might say, well, what's happening to y? Move this point along the way. And one of the things that we learn in Math 30-1 is mapping notation. So to look at mapping this point along its actual path and asking, well, what's actually happening? So I am going to do the one thing that's kind of sitting in the back of my mind right now, and that is factoring out that 3. I guess I don't really need this bracket there. Factor out this 3. Now we do want to factor out that 3 to properly notice the horizontal shift is actually 4 units to the left instead of adding 12 or moving 12 units. It's actually a 4. So I've got this a little bit more tidy up, and I ask what's actually happening to x. So all the x, y values are being mapped onto what's actually happening. There is a horizontal stretch by a factor of 1/3. So we would be multiplying all the x values by 1/3, and then we would be moving all the points left 4. We'd be taking off 4. So this is what should happen to every x value, every point. Okay. The y values, what we've got happening here is a vertical stretch by a factor of 1/2. So we're actually multiplying every y value by 1/2, and then we're going down 1 with that vertical shift at the end. So I can actually take any x value, like if I really wanted to take a 3 or a -5 and see where it goes. Hoping for, I can take any x value like -3 and see where it goes. Hoping that it's either a 3 or a -5, and then feeling a little bit confident if one of those works out. Okay, so let's take the point A at -3 and see where it goes. If I plug in a -3, let's see where this point goes. So I've got a 1/3 times a -3. That leaves me with a -1. Subtract 4. That leaves me with a -5. So this point should have an x value of -5. Good. That feels good because C and D both have this as an option. As we look at the y values, one of my, again, concerns would be making sure that positive 12 isn't used, and they are using this -4 for this horizontal shift. So with the y values, though, we've got starting off at a 4 and seeing where we end up. So we've got a 1/2 stretching by that y value of 4, and then we're taking off 1. So 4 times a half is a 2. Take off that 1, and we're left with a 1. So hoping for a -5, 1 as a potential location of this transformed point, and conveniently I do see this option C as that choice. So in this case, the mapping notation, what's truly happening, allowed me to procedurally figure that out. Okay, let's move on from number 4 in the multiple choice to multiple choice 5. Now this one shows the graph of y equals f of x is shown below, and I'm noticing this is now a polynomial function, opens toward the down direction, so there's a negative a value happening here, and I'm noticing a lot of curves in there, so it's probably got a few degrees or multiplicities happening here. So this question, though, says the number of points that would be invariant. Invariant referring to points that would not move after a transformation or some changes applied to it. Does not move. So what's not going to move when the graph y equals f of x is reflected in the line y equals x? So y equals x is this line that travels right through the origin with a slope of 1. And I'm noticing the scale is, every tick mark represents 1 unit, so I'm feeling confident that this does have that 45-degree angle diagonally right through that middle. And so as I look at the reflection along the y equals x line, this is that diagonal reflection where anything along the reflection line is considered an invariant point. And I'm noticing that based on the end behavior and the trend in this graph, that there should only be 2 invariant points with a b value 5. For b, the answer is B for 2 invariant points. Okay, number 6. A restriction on the domain of the graph of the quadratic function f of x is a, x minus c squared plus d. That would ensure that the inverse y equals f of x is always a function is. Again, we're seeing this inverse language show up now. We are doing an inverse in this previous graph. That reflection is the inverse. That switching of the x and the y, this is the inverse. So we're talking in number 5 about this reflection along the line y equals x without referring to it as an inverse yet. But now we are talking about an inverse. So this question does have a lot of letters in it, a lot of parameters, but no numbers. But it's asking to restrict the domain on this quadratic so that the inverse is always a function. Now we don't know where this is, so I'm just going to draw a parabola in some place. And I did shift this up a little bit, right? And I don't even really know if there's any stretch to this, but we do know that the c value is the horizontal shift here. The d value is our vertical shift, and we're basically looking at some a that could make this a little more narrow or wider. So the question's asking, if we look at the inverse of this, if we do some diagonal flip, we're going to basically be looking at a graph that looks somewhat like a pair of those radical functions. It's this sideways parabola, which of course is not a function. We're basically looking to ask, how much would we have to ignore or restrict on the domain of the original function to say, you know what, if not all of this existed, if maybe only a little bit existed, it would pass the vertical line test. But maybe we could draw a little bit more. That much? No. How much would we have to restrict? And if we actually restrict half of this, this actually passes sort of a horizontal line test so that we could actually restrict the domain so that when it does flip, that horizontal line test sort of becomes a vertical line test. So if we restrict this domain to half of it based on the c value, we can say, all right, now it'll always be a function. So whether we restrict the left side or in this case, restrict the right side to say, okay, if only this part of the graph existed, great. If we restrict the domain based on a d value, doesn't really tell us anything about this domain because the d is attached to the y value, and how high this goes doesn't really tell us about how much horizontally to restrict. Okay. One of the most commonly misinterpreted answers is x is greater than or equal to c. If we think about parabolas at the center, if this was drawn right at the origin, it would definitely make sense to restrict based on just that middle portion. But because this could be shifted left or right somewhere, we have to consider that vertex of the parabola. Number 17, again, I'm seeing this notation just as I'm glancing. F to that little -1 exponent, that again is this notation for an inverse here. So we're going to be looking for more inverse logic here. And in this case, we're asked if we're given a function, f of x is 4 times 1/3 to the power of x minus 16. The y-intercept of the graph of this inverse to the nearest hundredth is. Okay, so it is important to know that an inverse is this reflection along this diagonal line. It is the switching of the x and the y, and there's a lot of different notations to it. But I will sort of remind you that x is equal to f of y is another way that we can see this, which is again this backwards logic to the switching of the x and the y. So I'm actually going to remind us that we can switch the x and the y, and this would create the inverse. So given the function, the y-intercept of the inverse is, I'm actually going to go right ahead and switch the x and the y. So instead of this being a y equals, I'm going to say this is an x is equal to 4 times 1/3 to the power of y minus 16. And now at this point, we have the inverse. It's not written in a very convenient way, but this is the inverse. This is asking for the y-intercept. Okay, so the y-intercept occurs when x is 0. So I can say x is 0, and let's now isolate y to figure out the y-intercept. So I can add the 16 over. I can then divide both sides by the 4. And then we can figure out, okay, how do I figure out that y value? We could go to logs and try to do some logs. We could also go straight to our calculator if we really, really wanted to. And we could say, all right, well, let's just, because this is machine scored, multiple choice, we can say one graph is a 4, another graph is a 1/3 to the power of our input, our variable, and I'll just say y, and we'll graph this to see if it conveniently shows up. There's the 4, there's the decreasing 1/3 to the power of our value, and a second trace intersect, down to number 5. First curve, second curve, guess, gives us a y value of -1.26. I'm seeing that option A as our nice choice. So -1.26 as our graphical solution to do this. Because they are decimals, I'm assuming that this is not going to be some algebraic approach. But again, we could have went into logs and said, all right, 1/3 to the power of y is a 4. So we could have said 1/3 to the power of y is a 4. And we could have evaluated this as log change of base, 1/3 of a 4 should give us that y value. And if we do want to just test that out, we could go into our change of base and try that out. So log base 1/3. Throw in some brackets there just to make sure. Input of 4, just making sure we can see this. Log base 1/3 of 4. This should spit out our -1.26 that we're also looking for. Now there are many ways that we can approach these questions, and I initially approached this by saying, let's create the inverse function and then plug in our values. Not the only way you may have done this, but that's why it's a good attempt if you try this first before we get into this together. We're into our first numeric response question, and so you are noticing now that the multiple choice and the numeric response are mixed together. and that's going to happen, but your machine scored section is going to have two different kind of sections. There'll be the multiple choice, and there's also going to be the numerical response that follow. So you're going to have to look for the numerical response boxes after. Okay, so number one, if log base 2 of k is 1/2 and cosecant theta is k, and our angle is between 90 and 270, then the value of theta to the nearest degree is, and this feels very much like that first question where we've got some equation with a k value. Everything is completed in there, but k is missing. And then in the next one, we've got cosecant of theta we don't know equals k, which we don't know. And so this very much, again, feels like we've got information in the first equation. Second equation is missing too much information to do anything with it to figure out theta. So in my mind, I'm saying, let's figure out k, put it into the second one, and then figure out the value of theta that we need. So in my brain, my game plan is get k, then get theta. All right, so let's figure out what we can about k. We know that log base 2 of k is 1/2. All right, so I can do that change of base to say 2 to the power of 1/2 is k. 2 to the power of 1/2 is k. I can get this k value by, well, basically considering that 1/2 as a square root, because an exponent of 1/2 is the same as a square root. So instead of getting this to a decimal, I might actually leave this as a k value that's isolated by itself already. It's a root 2. So I can now say cosecant of theta is k. And I know that cosecant of theta, even if we go to our formula sheet here, cosecant is 1 over sine. So now we're into the reciprocal, where I can say 1 over sine is root 2. Or I can reciprocate that root 2 and change it to 1 over root 2. So there's a little bit of logic in here which you may want to pause on and just think about. But now I know that sine of theta is 1/2. And I'm looking for the angle between 90 degrees and 270. So 270 down here. So my answer has to be somewhere in that shaded orange region. When is sine of theta 1 over root 2? Well, sine of theta is 1 over root 2 at a positive value here and here. And the only one that actually makes sense is this terminal arm in quadrant 2, this top left corner. So we have a 1 over root 2 reference angle at 45 degrees. But we're not asked for the reference angle, we're asking for the angle in standard position here. So we do have to take this rotation all the way to there, 180 minus 45, and we do have that 135 degrees. So our answer would go onto the bubble sheet in degrees as 135. So again, we're seeing this logic of determine a missing value and use it later on. All right, our next one, back to multiple choice number 8. If log base 3 of 5 is 3y and log base 3 of 4 is 2x, and log base 3 of m squared is 6, then we've got this big log base 3 of 100 m to the power of 4 is equivalent to some algebraic kind of expression we've got. Okay, so when I look at a question like this, I'm staring down this part. This is our heart, where we need to make this equate to our answer. And all of this previous information, these 3 expressions at the very, very beginning, these equations at the beginning, somehow we need to use those. But my brain is sort of locked in on this log base 3 of 100 m to the power of 4. Now, this is a conceptual question where we can't really use our calculator and procedurally punch things in. We're basically looking to use the log rules, tear it apart, and somehow make an expression out of these equations. So I'm going to start with this heart log base 3 of 100 m to the power of 4. And what I want to do for this is try to break it apart and create these previous expressions. I want to create these previous equations. So I need to somehow find a log base 3 of 5 in here. I need to find a log base 3 of 4. I need to find a log base 3 of m squared. So I need to break this apart. Now I do know that in my log rules, I can break this apart and turn this into a log base 3 of 100. And I can add this together with a log base 3 of m to the power of 4. And I can separate this product in the input into an addition of separate logs. And this is one of our log rules. So right here we've got log base b of mn can be turned into two separate logs. All right, let's jump back out and look at how we can maybe make log base 3 of 5 and a log base 3 of 4. Well, I can maybe turn this 100 into another product of two things. Can I make this into a 20 times a 4? Would that help us out? Now I am thinking if I made this, I could say 25 by 4, 20 by 5. There's a lot, a 10 by 10. I have a lot of choices here. Let me just test something out and see what happens if I do a log base 3 of 25 by 4. So I can separate this then into a log base 3 of 25 by 4. That should make 100. Now, does a log base 3 of 4 help me out? Well, I do see a log base 3 of 4 as one of my options, and that kind of does help me out a little bit. I don't see a log base 3 of 25, but I do see a 5, and maybe I can deal with a 5 squared or something happening in there. So I'm going to stick with this for just a moment and see how this plays out. But there might be a little bit of choice in here to try to get to a good place because we did have choice. And I'm not going to forget about this log base 3 of m to the power of 4. Although while I'm writing this, I am noticing that an m squared would really, really, really be helpful. So I might change this to an m squared squared. And then I'm already thinking, before I'm getting ahead of myself, that power of a 2 that's on the entire input could maybe shift down in front and change from an exponent or a power into a product, hanging out in front as a coefficient. We'll drop that down in the next one. Actually, we'll write that here just while it's on our brain. All right, so I'm feeling like that might be a helpful step because we can then say there's a 2 hanging out in front of a log base 3 of m squared. What's a log base 3 of m squared? It's a 6. So let's just change it to a 6. So 2 times 6, that should be a plus 12 at the end. All right. Well, I'm actually only seeing a plus 12 once in all those choices. So I'm feeling like the answer is going to be B, but just to make sure, I do want to double check a few of these things. A log base 3 of 4, I am seeing that match over here, log base 3 of 4, that I can replace with a 2x. So let's swap that out with a 2x and see if that's kind of matching our confirmed choices. It is. And so I'm feeling, again, fairly confident at this point. But this log base 3 of 25, I need a log base 3 of 5. So again, I'm going to use these log properties to say log base 3 of 5 squared and change that squared to be a coefficient in front, log base 3 of 5. And a log base 3 of 5 I know is 3y. So I can swap out that log base 3 of 5 with a 3y. And we do in fact know that that makes a 6y plus a 2x plus a 12, kind of leading us to that final answer, B, which I'm, again, far more confident in now. Okay, moving on to our number 9. The expression log base a of b plus 4 log base a of ac minus 4, written as a single logarithm is, more log rules. And the a, b, and the c greater than 1, it kind of implies that we can't have a negative base, which is sort of a rule. And then there's some conditions about the b value and c value being greater than 1, which don't impact this. It looks more like the log rules that we're trying to work with. So I do know that when we are adding logs together with the same base, we can write those together as a single product. So log base A of, but I did notice that there's this 4 hanging out in front, and all of a sudden we cannot do this. So we need to rethink this for a moment and say, how do I deal with this 4 which is just in the way? So I might need to move that up and shift it back into that power position on that 4. One of the things that makes me nervous about that is where that 4 gets applied only to the C or to the A and the C. And as I look at the choices, I'm curious if one of the options is going to have A without the 4. And am I seeing an A? The A has a 4. There's an A on the bottom. I'm seeing some without A's. This is going to be interesting just to see what kind of happens here. So let's tidy this up a little bit. Now that we have a log base A of, there is a B. I guess there's no division just yet. So there is a B, and I'm going to multiply this by, there is an AC to the power of 4. And I'm going to give that A a power of 4 and the C a power of 4. And then I'll even maybe get rid of that multiplication for a moment. And we're subtracting 4. Subtracting 4. And as I look at all the options, there is no subtracting of 4. But what we do know with logarithms is that we can introduce log base A of A, which has the value of 1. Remember, log base A of A is a 1 because A to the power of 1 is A. So what we've got here is a little introduction of a log base A of A. It's the value of 1, and now we have a matching base, a log base A. This 4 can shift up as a power on that input to say log base A of A to the power of 4, and we have this log base A of, well, it doesn't look like this is in numerical order in our choices, so I'll keep this as is. And because we are now subtracting, we can now turn this into a division on the input. So we've got a log base A of, let's make this a very large input here. We are subtracting, so there's a division. All right, what's on the top? Anything with a positive coefficient in front goes on the top. B, A to the 4, C to the 4. Anything that we're subtracting or has a negative in front, a negative coefficient, shoots down to the bottom. A to the power of 4, and that's maybe where it's coming from. Those A to the 4s do end up canceling, leaving us with a final answer, log base A of B, C to the power of 4. Looking at our options, log base A of B, C to the power of 4. The answer is C. All right, this next one, as we look at another visual here, this says the graph of log base B of x plus c, shown below, passes through the points 0, 0, and a 3/2, comma 1/2. And then it says the value of b to the nearest hundredth is. The value of b to the nearest hundredth. As I look at this, again, this very much seems like two pieces of information. It goes through 0, 0, and a 3/2, 1/2. Often when you look at these, you might try to guess and check your way into saying, how can I make this graph go through 0, 0, and you'll guess at a base, you'll guess at a c value because there's only two pieces to this. But what can we do that maybe kind of gets us closer? Now you might say, well, I can plug one of these points into our function and hope that something works out. Maybe it kind of tidies up nicely. And that's maybe where the 0, 0 comes in. It would be very nice if we plugged in a point that worked with this equation, and it actually gave us a bit of information. Sometimes that's the intent. What I'm going to do here is I'm going to plug in 0, 0 into this equation, where there's a y equals log base b of x plus c, and I'm going to see if 0, 0 helps us out. A 0 comes out when a 0 is plugged in, 0 plus c. That's actually kind of nice because if we consider this change of base from a log to an exponent, I can say b to the power of 0 is c. And anything to the power of 0 is a 1. We just figured out that the c value is 1. This has shifted 1 unit to the left. Beautiful. So the information that we now have is that y is equal to log base b of x plus c, and c is in fact 1. So the only other piece of information we have is this point, 3/2, 1/2. And if we plug in those points into that point into the x and y, we hopefully should be able to isolate the value of b to the nearest hundredth. So our y value is 1/2 when we plug in 3/2. So let's plug in 3/2 and see how this tidies up. Now I did run myself into a corner with space here, so I'm going to just move this over a little bit so we can see this nicely. And we'll do a little bit of fraction work here in the corner. Log base b of 3/2 plus 1/2. So 3/2 plus 2/2 gives us a 5/2. And now we can again apply this change of base formula to say b to the power of 1/2 is 5/2. All right. How do we get b by itself if we've got a power of 1/2? Well, we can apply a squaring to both sides. And the opposite of this square root on the b is to square both sides. So regardless, we do have to square both sides to get this b by itself. And what we end up with is 5 squared over 2 squared. And this is a little bit more than 24 divided by 4. It's a little bit more. It is a quarter more, so it's a 6.25. Again, use your calculator to double check, with a 6.25 as a b value to the nearest hundredth. So again, this is one of those cases where we've seen this multiple times already. Two separate pieces of context, one with a little bit of information applies to help out with the next calculation, and again, works out very procedurally after that. Next question, number 10. And again, if you haven't been pausing, give it a pause, attempt the questions, and see if you can figure it out first. Given y is equal to a to the power of x divided by a to the power of 2x minus 6, and we've also got a log base a of y is x, and that base a is greater than 1, then the value of x is, and there's either one answer or two answers. When I look at this first expression, this feels very much like your grade 10, Math 10C power rules, where you're looking at that division with the same base. So why not say it's an a to the x, subtract a 2x minus 6. We could make this way cleaner and make this a single base. A to the power of x minus 2x is a negative 1x. Now that negative does have to distribute in, so we do have a plus 6 that's hanging out afterwards. And that's kind of what we've got. And we also know that log base a of y is x. Okay, so we do have something with a bunch of parameters. I'm going to do a little bit of thinking over here. And if I could get this y by itself, we might be able to make a set of equations where y is this and y is this, piece it together, and you have it all coming together. So change of base formula says a to the power of x is y. A to the x is y. And if y is a to the power of x, but a is also negative x plus b, we do have a set of matching bases to therefore say all that really matters here are those exponents. So we should be able to say that x is negative x plus b, and that if we add the negative x over to the right side, so add an x to both sides, we should end up with a 2x is b, 6, thank you, 2x is 6, and x is in fact a 3. Final answer, A. All right, moving on to after number 10, numerical response. Use the following information to answer numerical response. Number 3, Joe invested $4,500 at a fixed annual rate compounded annually. And I see that annually, and I'm a little bit relieved because if it was compounded in a different way, there's a little bit more work to it. At the end of 12 years, the investment has doubled in value. To the nearest 100th of a percent, Joe's investment pays interest at blank percent per year. Okay, so we're looking for this interest rate, the base or the b value. Now we do have this a times b to the power of, I'll go right to the formula sheet and show it what we're referring to right now. We do have this growth and decay formula, a to the power, a times b to the power of t over p. And if there was a change in this compounding, we'd have to deal with that. But right now, kind of conveniently, we don't have to worry about a compounding semi-annually or something like that. So we do know that Joe invested some money and it doubles. So $9,000 comes out when the original $4,500 was invested. I don't really know the 1 plus the interest rate, the I value, but I do know that after 12 years, something has happened. So again, this is compounded annually, so we don't have to worry about some t over 2 for semi-annually or something like that. So we can divide both sides by 4,500 to get a 2 is equal to b to the power of 12. Basically, we're looking for that b value. So we can either do this graphically or we can try to do this a little bit algebraically. We can try to do, you know, a 12th root if we really wanted to, like 12th root of both sides to say what's the 12th root of 2. Calculator is pretty easy as well. We already have this sort of logic applied earlier. So I'm going to say one of the equations or sides is 2. The other one is a value to the power of 12. And so we have to intersect these two things. Just graph these and see if they show up. There's a 2 that shoots across. There's a base to the value of 12. And we're looking for a positive value here. So let's do a second trace. Number 5, intersect. And we're looking for a first curve, second curve, guess, and 1.05946. So B is a 1.05946 as our B value. So this is not increasing 106%. This is increasing by 0.05946, or this 5.94%. So to the nearest 100th of a percent, we're going to say this is 5.94, 5.95%, because that 6 rounds it up. So this is paying at 5.95%. And just to double check, if we did instead do a 12th root of both sides, we can hopefully confirm that our math is correct, to the power of 1/12th to the power of 1/12th. So whether we do a 12th root or we do a power of 1/12th, let's just double check this. 2 to the power of 1 over 12. We end up with 1.05946. So I'm going to take off that 1, and I'm going to multiply this by 100 to get me right to 100%. Right into a percentage, 5.95. All right, so I'm feeling again better about that, applying that in a non-graphical way. Okay, let's move on from our numeric response 3 into our question 11 multiple choice. In order to factor the polynomial p of x is 3x plus 3x to the power of 3 minus 2x squared minus 19x minus 6, a student determined that the function has a 0, x-intercept root has a 0 of x is 3. He then wrote the polynomial as a product of a linear factor and a quadratic factor as shown below, where a, b, and c are integers. All right, so this is telling us we can't have a's, b's, and c's be decimals or fractions. So we are limited to integral values here. So which of the following are the correct values of a and b? A and b. So I do know that one of the roots or one of the zeros here is x is equal to 3. So this should say x minus 3. Or if we want to keep this as a plus, x minus a negative 3. That'll make it say plus. So correct that right there. This should say x minus 3. So if we want to make it look very, very similar, we could say, well, you're adding negative 3. So our a value is negative 3. And this is, again, one of those super careful things. For the 0 of x equals 3, it should say x minus 3. Okay. Now, the one thing that we can't really do very well, we can't actually just go to our calculator and figure out our roots or our zeros because we're not actually asked for our x-intercepts. We're asked for parts of a quadratic. So we do need to go in and do a little bit of maybe synthetic division to break this down. Now, there's more than one way to do synthetic division, and so this is going to be a little different based on what's kind of happening in your classroom. So we've got 3x squared minus 2x squared minus 19x minus 6, and we're going to be dividing by the factor x minus 3. Now, again, I'm going to be doing the synthetic division with some subtraction, and I'll comment on that it can be done as well with addition as well. So this is going to sort of parallel our long division, but here we're going through our synthetic division, and I will be using subtraction for this one. So the 3 drops down, we multiply the negative 3 times the 3, and we end up with a negative 9, and we subtract. Multiply, subtract, multiply, subtract. And a 0 remainder is great news because that means the x minus 3 factor, or the root x equals 3, worked. So I know that the power decreased from a cubic function to a squared, and what we're left with is 7x squared, 3x squared plus 7x plus 2, which confirms that 3 up there, but our b value here, this coefficient on our x term, is a 7, and so that leaves me with that b choice. If we were to do this with not subtraction, and not to again mess anyone up here, but for some schools, for some teachers, for some students, they prefer addition because there's less concern about the subtracting of negatives. They'll say, all right, we're dealing with a 3, negative 2, negative 19, negative 6. That is not impacted, that's the same. We're dealing with x equals 3, and instead of subtracting, we are adding. So multiply, add, multiply, add, multiply, add, and we still end up with that same answer, but this time we did it with addition. So pick your one way that works, that makes sense, and stick with it. Remembering that this is not x plus 3, it's still the x minus 3. So this was set up in a different way, which we just have to make sure we are interpreting it properly. So that is multiple choice 11, option B. Our next one here is a question 12. A particular polynomial function has the following characteristics. There is a factor of x plus 2 with a multiplicity of 3. Ooh. So we are dealing with an inflection point at x plus 2, x equals negative 2. And there is an inflection point. So that could look like this. It could look like this. We don't really know that direction just yet. It does say, though, that there is a, when you plug in a 0, there is a y-intercept of negative 24. So this does exist down here at a negative 24. And there's a minimum value of negative 66. So somewhere our graph is hanging out down here at negative 66, not to scale at all. But this question then says, in a SEM, for the polynomial function described above, the minimum possible degree is blank, and the leading coefficient is blank. Minimum possible degree. Well, if this is kind of curving down, and at some point it's reaching here, and then it actually has a minimum value of negative 66. That means it has to curve up at some point and maybe do that. My guess is it's going to look something like this, which implies we've got a multiplicity of 3 here. So there's a degree of 3 coming from that, and another degree coming from this right side over here. And so another 1 from there. So a 3 plus a 1, this is a minimum, it has to be a 4. Nothing in here tells me that there's more than a 4, that it's a 5. So it could be that. I'm trying to think then, could it do something like this direction? I mean, negative 66 at the bottom then implies it has to curve up at some point, but then how's it going to get down to a negative 24 and then back up? That implies, you've got another multiplicity over here. So 1 and 2, 3, 4, 5 and 6, or maybe this just curves down. Either way, we've got way too many things happening with this scenario, and I'm feeling like this visual, this setup wouldn't really work very well, and it's probably more likely this one. So if we've got a minimum degree of 4, this is opening in the up direction, so you're going from quadrant 2 to quadrant 1, opens up, right? So that means it's a positive leading coefficient. If it was negative, it would be going in the downward direction, but the information here implies that this is positive, so we're going to go with option A. Number 13. Okay, so a numerical response number 4. So this question says the graph of a polynomial function has integral x and y intercepts. Nice. The equation of the function can be written in the form, it's all multiplied together, where a, b, c, and d are elements of the integers. So no fractions or decimals for our coefficients. And then we've got, I'm staring this down and I'm seeing those exponents of 2, the multiplicities are 2, and I'm not seeing any other information other than that. And because they are multiplicities of 2, or they're degrees of 2, it does make sense that this is a power of 4, in fact. So let's see what we're being asked to do with this quartic function. In the equation above, the values of a and e, a and e, a and e. So we're looking for the a value and the constant. Okay, well, let's see what we can do to piece this together. I do know that this has to take the form of a with something squared, and this is going through -1, so this should say x plus 1. And this should say an x minus 2 to go through a 2. Now I know that there's really not a lot more happening here, but I also know that this graph could look more like this, depending on how much that stretch impacts this vertically, not horizontally, but how much it impacts that vertically. So I might be a little bit nervous about saying, that's it, and this is the function. I might say, I'm going to throw in a stretch there just in case it's not a 1, and say, I need to have one point on here that forces this through a very, very specific place. So I'm going to plug in a single x comma y point to say, let's fix this stretch. And I'm going to pick on this y-intercept of 8. So if I plug in an x value of 0, an 8 should come out. If I plug in an x value of 0, 0 plus 1, and I plug in a 0 minus 2, I should be able to work myself to figure out what this a value is. So 8 is a times 1 squared, right, a 1, times a -2 squared is a positive 4 times the a. Divide both sides by 4, and we do end up with a is 2. So a is 2. Good information. That's not the final answer, but we do know that if I take this a value of 2, erase, 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 take this all back to the beginning here, and I say, if this a value is 2, and I were to multiply this whole thing out, what would these two values of a and e be? Now, I don't have to do all of that because I'm not really looking for every single x squared and x cubed term. I'm really only looking for the first one that is created from the x to the 4 and that constant at the very, very end. So I do know that if I did expand that x plus 1 squared, I'd end up with an x squared plus a 2x plus a 1, and then eventually I'd end up with an x squared plus some other things. I'm really most concerned about that very first term. X squared times the x squared, you're going to have your x to the 4 show up there, and the only thing that's going to happen is that 2 is going to later multiply into that. And so you are going to eventually have a 2x to the power of 4 that shows up. So I'm feeling confident enough to say I'm not going to do all this work. I know that a is 2. Okay, let's take this back and say a should be a 2. And I'm really not going to do any more work than that. The last value, this e, where is the constant term created from? Well, it's created from the constants multiplying by the constants. I do have to do a little bit of work in here, dot, 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 to eventually say there's going to be a 1 times a 1 that shows up. I'll just show it for the first one. You know, you're multiplying x plus 1 times x plus 1. There is going to be a 1 times a 1 that eventually happens, and some other terms. But I'm going to say dot, dot, dot. Let's just really focus on there's some things happening and a 1. And in this last one, there's going to be an x squared. There's going to be minus a 2x minus a 2x plus a 4. So there's going to be some things happening plus a 4. There's going to be lots of multiplication that's happening. What I'm most concerned about is the very last term is going to be created from a 1 times a 4. So there's going to be lots of stuff happening here, and there's going to be a plus 4 when this 1 and 4 connect. And in the end, that 2 distributes into all those terms, and you're going to be left with a 2 times a 4 creates an 8 at the very, very end. So I know this is somewhat, we'll say lazy, but maybe it's more strategic to say I'm getting the information that I need. Okay, so we've got a 8 showing up as our e value, and that is our end. So let's move on from our 2, 8 to a graph of f of x is shown below. This is multiple choice 13. The graph of f of x is shown below. The graph of the square root of f of x is to be drawn on the same coordinate plane. So we're basically square rooting every y value. We're square rooting f of x. And this is somewhat deceptive if you're not feeling very confident and you're using your calculator to do this. There's some deception that can kind of happen here. But ultimately, the graph of the function y equals square root of f of x will have a domain of some choices. And there are 2 invariant points associated with this transformation. So let's try to figure out the domain and how many invariant points are going to be associated with this. So let's consider what the square root of this function is. Now if we square root all these y values, pretend this is a 9, it square roots down to a 3. If this is a 4 somewhere around here, it square roots down to a 2. Square root of 1 is a 1. Square root of 0 is a 0. And you'll end up with something kind of like this. And it'll kind of shift that way. These y values are all negative. Negative 1, negative 2, whatever they are. So they're not going to actually be able to exist. The square root of all these negative values don't exist. But the square root of these positive y values, square root of 0 is 0. Hey, that's invariant. Square root of 1 is 1. Hey, that's invariant. Square root of 4, somewhere up here, is just down to a 2. Square root of 9 is a 3. And eventually you'll get this very similar but symmetrical shape about this. So our graph will look something like this if we sketch this. Where does this exist? It exists from b to the right, and it exists from negative a to the left. So we're looking for a domain to be everything left of the negative a and everything right of the b. So we're not talking about between the values. It doesn't exist there. It's less than a, greater than or equal to b. Less than or equal to negative a, greater than or equal to b. How many invariant points are there? Well, there are only a couple of key places where invariant points occur, and that's where it doesn't move. And for a square root of a function, the square root of 0, when y is 0, the square root of 0 is 0, The square root of 1 is 1, and that happens when y is 0 and when y is 1, and that happens in 4 places. So 4 places, option A. One of the things that if people are not feeling like they remember square root functions, they'll often go straight to their calculator, and they'll go and they'll graph something that's kind of what they can best approximate to be a square root of a quadratic function, like, let's go the square root of, and let's just draw one that's sort of shifted down a little bit, x squared minus 4. And they'll say, okay, well, here's the square root function. What does it look like? And say, all right, well, how far down does that go? Like, does it exist at negative a and b? And maybe they even click zoom in, and they're trying to figure out where this exists. And they'll zoom in again. And they're saying, like, does it actually get down to that x-axis? And again, you can try to zoom in as much as you want, but this is a pixel problem. Don't trust the calculator on how far down this goes. It actually gets to those x-axes, those roots and zeros. It gets there. So don't assume that it's stopping because of pixels. All right, so let's jump on after this multiple choice 13 onto a rational equation. The vertical asymptote of the graph of the rational function is defined by the equation x equals k. The vertical asymptote. The value of k to the nearest hundred is. All right. So we're thinking about what happens with rational functions. And my brain first goes to, well, we got to factor these, the top and the bottom here, and see where this, if anything matches. Because if there's a factor on the top that matches the bottom, then we've got a point of discontinuity. And then if there's a factor that's only on the bottom, we're looking at a vertical asymptote. And if there's a factor that's only on the top, there's your x-intercept. But maybe we're looking for a vertical asymptote. We're looking for a factor that's only on the bottom. Well, to figure that out, let's start doing some factoring. So depending on whether you're using decomposition or this box, lucky, logical approach, you might factor this in a different way, but I already know a little bit of information about this. So I know that the factors for that negative 10 are probably going to be a negative 5 and a positive 2 based on that negative 3. We factor that, we're good. Now, in this course, we know that we're sometimes dealing with a factor on the top that matches the bottom. In my heart, I'm thinking, all right, I need one of these factors to be on the bottom if we're only going to have one vertical asymptote. When I look at that 18, I'm thinking, all right, what's going to create that 18? Is it going to be that 5 or the 2? So I'm thinking, well, one of the factors is probably going to be an x plus 2. I'm not guessing just yet. I'm going to use a little bit of logic to do this. So instead of doing a full figure this out on the side, I'm just going to say, well, a 4x times the 1x would make this. Cool. What would make that negative 18? Well, probably a negative 9 times a positive 2. Okay, well, let's just double check that this is right. Positive 4x squared, good. We've got a negative 18, good. Let's just double check the middle. And I'm, again, feeling like this is probably going to be our answer, but there's going to be a positive 8x, and there's going to be a negative 9x, and this does create that negative x in the middle. So I'm feeling like I didn't really need to do as much procedural work if I kind of trusted that one of these is going to work. Okay, so point of discontinuity is that x equals negative 2. Great. There is a vertical asymptote at our other factor, 4x minus 9. So the 4x minus 9 is not allowed to be 0. So, and maybe by defining this as it's not allowed to be 0, we'll just say, well, where is the vertical asymptote? And we'll make this an equation. So 4x is 9, and therefore x is 9 divided by 4. So 9 divided by 4, again, 8 divided by 4 is 2, but we're going up a 1 over 4, so we're looking at a 2.25. Again, test your calculator just to make sure. Stakes are high. So 2.25. And there's our vertical asymptote. Sliding on to another rational equation. This one says the graph of g of x is shown and can be put into this form with some transformations. The function is defined by, the function f of x is defined by some sort of quadratic. So we've got a rational and a quadratic. And ultimately it says the domain of the function h of x, ooh, a composition, is g of f of x. So let's try to wrap our head around this as you pause the video and give it a try. We're looking at h of x as being defined by g of f of x. So my brain goes to f is going into g. This quadratic is going into g. And then it's asking for the domain of the function having a restriction. So when we look at a composition of a function, the input goes into the x value of the outer function. So the function g is made up of, I'm just going to write this down here, sum a over x minus b plus c. Now what we do with a composition is we plug the function f of x into the input of g. So it says x minus b. I'm going to replace that x with x squared plus 3x minus a 4. Let's just zoom in a little bit here. So the x changed, and we still have this minus b that we can't really forget about. So minus a b. Apologies for that stretching over. But we don't know b. What is b? Well, b is the horizontal shift for function g. This is shifting 6 units to the right. Awesome. That's simple. So that b is shifting 6 units to the right. So I can just say minus 6. Let's really just focus in on what this is saying for now. So what we have is some a value, which I don't even know if I need that right now. There is a vertical stretch on this rational function. But on the bottom here, I've got an x squared. All right, we've got an, hold on. We've got an x squared, there we go, plus a 3x minus a 4 minus a 6. Minus a 4 minus a 6. That's a minus a 10. Okay, so minus a 10. Minus a 10. Okay, so what I'm thinking we could do is we could actually take this and figure out, and there's a plus c over here. There's a vertical shift that's happening. But I'm not too concerned about that because that shouldn't really contribute to our restriction. Where can we not allow this to go? The domain for this denominator, the values for x that don't work, is going to contribute to our restriction. So let's factor this denominator and say, all right, x plus 5 times x minus 2, and then there's again going to be this plus c. This is going to tell us that, well, you can't really have a negative 5 or a positive 2. Not allowed. This should be the restrictions for our composition of g of f of x. And so I thankfully see that as option D in number 14. Okay, well, let's move on. We're maybe getting into some angle stuff again. Circular carousel has a diameter of 22 meters. An adult standing on the outer edge of the spinning carousel. Okay, so there's a person standing on the outer edge of this carousel, and it says the central angle formed when the adult travels 10 meters. Let's go to a top view of a circle. That's a circle, by the way. When the adult travels 10 meters. Okay, so person travels around the outside 10 meters. What is the central angle? Okay, well, on our formula sheet, we do have a defined formula which says theta in radians is the arc length divided by the radius. So our central angle is defined as the arc length, or that distance around the circumference divided by our radius. And we have a little bit more information. I'm assuming a diameter of 22, which means our radius is 11. So what is theta for an arc length traveled 10 meters divided by a radius of 11 meters? Those meters will cancel. 10 divided by 11. So we are dealing with 10 divided by 11 radians. So the question is, though, in degrees. Great. This is one of those diploma questions where it asks you to go a little bit further. So how do you convert between radians and degrees? Lots of ways to convert. Some people say, all right, pi over 180 degrees is, let's relate this, and they say, all right, radians on the top, because pi is radians on the top, and you can say 10 divided by 11 radians is going to be our amount in degrees. Really, we could have also made this cross-multiplying a little bit easier if instead we had set this up differently to say, all right, well, let's put our 180 degrees on the top over pi radians, unknown degrees over 10 over 11 radians. That 10 over 11 slides up there, and our amount of degrees is going to be 180 times 10 over 11 dividing by pi. And that calculation, whatever it is, should turn into our value. Now again, there's many ways to convert between degrees and radians. Some people have it set up where they'll say pi radians is 180 degrees, draw a line on top of each, and the radians is on like the left side now. And so they'll say 10 over 11 radians is how many degrees, and degrees is on the right side. Cross multiply to slide that up there. And there's many ways you could set this up. Regardless, we've got this calculation which we need to do. So grabbing your calculator, we're looking at 180 multiplied by 10 divided by 11. And then again, we're dividing by pi, being very careful. We do end up with 52 degrees and some change. So 52 degrees and some change, thankfully, option C. From number 15, we move on to question 16, still in trig. The point T at root 3 over 2, 1/2. Ooh, this is nice values. I'm feeling like this is good at 30-degree reference angle. Feeling good about that. Is the point at intersection of the unit circle and the terminal arm of angle theta. Okay. If the angle of rotation is changed to become theta minus 3 pi over 2, then the coordinates of the point where the terminal arm intersects the unit circle will be. Okay, so it sounds like if we know theta is 30 degrees, or pi over 6, why not just change the location and back it off 3 pi over 2 and get to a new location and then figure out that point? So if we know that this is pi over 6 or 30 degrees, let's figure out this new location. So pi over 6, so this is the terminal arm at pi over 6. I'll zoom out so you can see this if you're, again, pausing. Take off 3 pi over 2. Let's just get this to a common denominator. So this location should now be pi over 6, take off 9 pi over 6. This location, again, we're subtracting this. So now we're at negative 8 pi over 6. And if we reduce that down, it's negative 4 pi over 3. Okay, so our new location is negative 4 pi over 3. Okay. So instead of starting at this place and backing off 3 pi over 2, we're just going to say, so instead of, again, starting here and backing off negative 3 pi over 2, so negative 1 pi over 2, negative 2 pi over 2, negative 3 pi over 2 should put us right around here. I'm instead going to say, well, let's just count negative 4 pi over 3, and I did a bit of fraction work instead. So we should end up at the same place here. But let's again get to negative 4 pi over 3, which is our 60-degree reference angle if it's over 3. So negative 1 pi over 3 negative 2 pi over 3, negative 3 pi over 3, negative 4 pi over 3. Great, it puts us at the same place, and so we do end up with negative 4 pi over 3 at this location. We still know that this is a 60-degree reference angle at negative 4 pi over 3, and that is the reversed version of those. So that is a 1/2 comma root 3 over 2, because the 30 and the 60 degrees are kind of mirrored or switched values of each other. The x value is negative, y value is positive. Looking for a negative 1/2 and a positive root 3 over 2. Option B does give us that new location at, which is identical to 120 degrees, or 2 pi over 3. After number 16, again, we're on to a numerical response number 6. The point A comma negative 2a, where a is positive, is the point of intersection between the terminal arm of an angle drawn in standard position and the unit circle. Okay, so there's a terminal arm meeting the unit circle. The value of a can be written in the form of m divided by root n, where m and n are single whole digit numbers. The values of m and n are. So it's kind of strange where we know that a, because that a is positive, we know that there's no trickiness with like a double negative in here. So I can say that a is somewhere positive, like here or here. I really don't know where it is, but the x value is positive. The y value is negative. The y value is negative, and it's a negative 2a. So it's a little bit more negative in the y side. But we're intersecting the unit circle. And what is this coordinate? What is this? The value of a. So we're kind of looking at this intersection of these two the intersection of these two things, and then figuring out what a is. Well, though we don't have an equation for the terminal arm, but we do have an equation for the unit circle. And the unit circle's equation is x squared plus y squared is equal to 1, or the radius squared, but in this case 1. And we do know a point that's on here. X value is a. The y value is a negative 2a. And we actually have one variable in an equation. And so hopefully if we can solve this, we should be able to figure out a. So we do have an a squared plus a negative 2 squared plus a 4a squared is equal to a 1. So there's 1a squared and there's 4a squareds. We've got 5a squareds, that is 1. And we've got an a squared that is a 1 over 5. And if we square root both sides, we end up with a positive or negative version of a square root of 1 is 1. Square root of 5 is a root 5. And because we were previously defined to say a has to be positive, I'm going to just erase that little negative there and say a is a 1 over root 5. I love that because when we say m divided by root n, and our answer is 1 over root 5, I know that m is a 1, n is a 5. And that completes my numeric response 6. Okay, moving on. We have a secant of theta being 13 over 12, and our angle is a bit bigger than 3 pi over 2 and 2 pi. Then the value of cosecant theta is. Again, one of these questions where you've got information, use it to answer some subsequent statement. So let's figure out what we can. We know that our angle has to be bigger than 3 pi over 2 and less than 2 pi. So we're sitting somewhere between 3 pi over 2 and 2 pi. We're in quadrant 4. So I'm going to scratch this off and say we got to be in quadrant 4. And we know that if secant of theta is 13 over 2, then cos of theta has to be a 12 over 13. So there is some triangle which can be defined in here where the adjacent is 12, that's opposite, where the adjacent is a 12 and the hypotenuse is a 13. I already know based on all these options that there's 5s, 13s, and probably this 12. that if I do a little Pythagoras, I'm probably going to end up with a 5, and in fact we do. 13 squared is 169, take off the 12 squared, 144, and you get a 25. The root 25 is a 5, and so a little Pythagoras gives us this 5, and we know that it's negative because we're traveling in the quadrant 4 down direction. So labeled sides in this specific location, this defines secant of theta is 12 over 13. This defines cos as 12 over 13, and secant of theta is 13 over 12 in this location. Great, we're set up. Now our question is, what is cosecant of theta? My brain immediately starts off with, well, this is connected to sine of theta. If I can figure out what sine of theta is, then I can flip it, that ratio, to get cosecant. Now, in this triangle, sine is the opposite over the hypotenuse, which tells me that if I reciprocate these values, I get a 13 over 5, still negative, and this should be my value for cosecant of theta. So let's try to find that negative 13 over 5 option. Negative 13 over 5 gives me option D as a beautiful choice. Moving on to number 18, we've got angles alpha and beta are drawn in standard position with the point -7, -4 on the terminal arm of angle alpha and the point 2, -1 on the terminal arm of angle B. Then what's the exact value of tan of alpha plus beta? When we have these operations in the angle position, that leads me to think we're dealing with some part of our sum difference formulas. So let's just see if we can find a tan of alpha plus beta. There it is. Tan of alpha plus beta is tan of A plus tan B. I'll pop that in here as an equation here. Tan of alpha plus beta is tan of alpha plus tan of beta, all divided by 1 minus tan alpha multiplied by tan of beta. Okay, this is what we need to determine. What do we know about these values? Well, we do know that -7, -4 is on the terminal arm of alpha of angle alpha. So let's just pause here and visualize this. What can we try to do with alpha? So -7, -4 puts us in this bottom corner here. And we do know that it's -7 to the left and -4 down. This is alpha. We'll label it as such. Beta is 2 to the right, 1 down. So 2 to the right, 1 down. And this is our angle beta. So from this left alpha triangle, I could go and I could find out, well, what is alpha? Second function tangent of negative of the opposite over adjacent. I could figure out alpha with Math 10C logic. But I can also make a statement and say, well, tan of alpha is opposite over adjacent. And if I divide those two negatives, I've got an expression for tan of alpha. I'm not actually going to get our angle. I'm going to bypass that and say, why not just swap out tan of alpha with a 4 over 7? And that's exactly what we're actually going to do. So I'm going to be rewriting this sum formula, and I'm going to be swapping out that tan of alpha with the entire ratio, 4 over 7. Tan of beta, well, we have to figure that out. Tan of beta is an opposite over an adjacent, so that's a -1/2. So not so bad. It's a nice number at least. And then on the bottom, we've got a 1 minus tan alpha multiplied by our tan beta. So this is not so bad. We'd have a little bit of fraction work to go about here. So on the very, very top, we're looking for a common denominator with a denominator of 14. So if we scale this up to, say, 8 over 14 plus a -7 over 14, we'll come back to that in just a moment. On the bottom, we've got a 1 subtracting. I'm already seeing they're subtracting. There's a negative product going to happen here, so I'll just change it to an addition. There's a 4 on the top and a 14 on the bottom. It's kind of nice. We might end up with a 14 denominator in both spots. So on the top, we've got an 8 minus a 7 is a 1 over 14. On the very bottom fraction, we've got a 14 over 14 plus a 4 over 14 is an 18 over 14. And if we divide these two fractions, we do have some canceling that will happen, and the final answer, 1 over 18, should result. And it does look like it's positive, and I am seeing an A option, 1 over 18, which when you're dividing fractions like that, there can be a little bit of nerves, but it's nice to see that answer show up. The exact value is. Okay, moving on. We've got a, looks like a Ferris wheel kind of question, sinusoidal functions. This question says, for number 19, an amusement park has 2 Ferris wheels that both load passengers at the bottom, 3 meters above the ground. Let's just see that. There it is, 3 meters above the ground. And both wheels require 40 seconds to complete 1 revolution. The larger Ferris wheel has a diameter of 25 meters, and the smaller Ferris wheel has a diameter of 10 meters. The height of a passenger on each wheel can be expressed in the form of, and there's a cosine function, all parameters there, where h of t is the height above the ground in meters, t seconds after the ride begins. So it looks like someone gets on the Ferris wheel, ride begins. Question is the 2 parameters that must be different. Good. Okay, so we're asking, what does A, B, C, and D do in this? Now, as I look at this, and I think about what's going to be happening as the person gets on and they'll ride around, what is that function going to look like if we visualize this? So I'm thinking it's going to look something like this for the larger one, and we'll just switch colors here and go for the smaller one. They get on, and they're going to do something like that. Now, what is the same? What's different? Well, I know already that both wheels require 40 seconds to complete 1 revolution. So the B value should be the same if the period is the same. So I'm going to look at the B value and scratch that off and say, not that. I'm looking at the C value maybe. They both get on at the same point on the bottom. So I'm thinking that the starting point should not be any different. And already I'm left with option B as my final answer. Does that make sense? Well, amplitude is probably the distance here from the center to the top. So your radius of the Ferris wheel is different, which then makes sense. And the midline, 25, midline 10, does make sense for that to be different as well. So A and D, both different. As we kind of confirmed, C and B should be the same. Number 20, the average temperature of a particular town in Alberta can be represented by the function T is 15.8, sine of, got a couple brackets here, pi over 6, open a bracket, T minus 3, close those all off, and then a plus 5, where T is the average temperature in degrees Celsius and T is the time in months after January 1. The minimum number of months to the nearest tenth of a month it takes for the average temperature to rise from 5 to 15. So I'm thinking with this, you're going to have some sinusoidal function. It's shifting 3 to the right and 5 up. I know my midline here is going to be at a 5. I know that. I really don't know where this sort of starts, but I'm feeling like it's rising and falling around this 5. So what is this graph going to do if we're asking how much time to go from 5 degrees to, I don't know where 15 is, 15. So I'm feeling like we're looking for this gap of time right here. How much time is it to go from a y value of 5 to a y value of 15? And this feels very much like a calculator question as an application. So I jump over to my calculator here, and what we're going to be looking for is plugging this in very carefully and making sure that we are, again, doing all these button presses appropriately. The one thing to always remember is that we are in a mode radians for any application question in sinusoidal functions. All right, let's jump into y equals and see if we can make this show up properly. So 15.8, we've got a sine of, the bracket opens up, so we're throwing in this pi over 6, closing that bracket, so opening a new bracket with this variable minus 3. And then we close off that horizontal shift portion, close off our angle, plus 5. Now, our window settings, we could try to quickly zoom this, but this is months. So I might go from 0 months to 12 months. For y values, these are temperature, so I might go from, just say 0 as a minimum. I don't really care about anything negative just at the moment. And a y value a bunch higher, say 25. Really, we're looking for a very specific section of this graph. We're looking for when the y value is 5, the y value is 15. So let's throw those in. When is the y value 5? And let's first figure that out. So throw that in, shoots across, and maybe we can throw in a 15 as well just to make sure. There's a 5 and there's a 15. Let's show both of these. All right, so we're looking for this first intersection followed by the second. As I do notice, the minimum number of months for the average temperature of the town to rise from 5 to 15. That's how I know it's the first section. So second, trace. Number 5, intersect. Let's just slide over to the very, very first position. First curve, second curve. My guess is that y equals 5, and I do have a value of x is 3. I'm not even writing that down just yet. Second, trace, intersect. First curve. Second curve. As you notice, I did have to select, because I've got 3 graphs happening right now, I did actually have to select my second curve. It was on the wrong one. And a guess, 4.3. So the 2 values were the 3 and a 4.3. So this is a 3 and a 4.3. So the time between those is 1.3 months. Feeling confident. Okay. Next one, we've got each of the following trigonometric expressions can be simplified to a numerical value where cos of theta is not 0 and sine of theta is not 0. That feels more like a restriction, just careful wording. So I'm seeing expression 1, 2, 3, some expressions. Using the expression numbers above, arrange the trigonometric expressions from lowest value to highest value, and which is the lowest and which is the highest based on the expression number. So I'm feeling like we do have to look at some of our identities here. So I might zoom in, move this over a little bit so we can see both at the same time here. And so what matters here? I'm seeing tan squared minus secant squared. So I'm looking for tans and secants. Is that double angle, some difference? Okay, I'm feeling like the 1 plus tan squared equals secant squared is going to be important. I can rearrange that to say tan squared minus secant squared equals -1. So if I rearrange this to say tan squared minus secant squared, this I can rewrite as a value of -1. And that might be something you want to write down and be very, very careful with. But I feel like I can say this value is -2. We've got a tan theta cos theta over sine theta. Well, I do know that tan theta is sine theta over cos theta. That's what tan is. But we've also got, I'm just going to extend this here, but we've also got a sine on the bottom, which should be able to just cancel, and a cos on the top, which should just cancel. This whole thing is 1. Okay. So it looks like the first one's an identity, and then we've got straight canceling, understanding the tan is sine over cos, and then we've got these reciprocal ones. So we've got a secant is a 1 over cos of theta minus a 1 over sine, and a cotan is not a sine over cos, but a cos over a sine. Now, there's lots of ways that we can try to tidy this up. The sines can cancel, And what we're left with is a 1 over cos minus a 1 over cos. Oh, we got a 0. So as we zoom out, I'm asking which is the lowest value, and that's a -2. So I use the expression number 1 to say -2 is the smallest, and then the 0 is the next one that's smallest. So I would say 3, and then 1 is the highest value, so that's a 2. That's a 2. Okay, so I would say it's a 1, 3, 2 in my numeric response bubbles. All right, the non-permissible values for x for the identity cosecant x tan x equals secant x are, so what are the non-permissible values? So I'm basically looking when are the denominators going to be 0. So we've got a 1 over sine of x, tan of x equals 1 over cos of x. Now, I know that those signs could cancel, but we do need to look at restrictions before the canceling occurs. So I'm looking at the sine of x on the bottom and a cos of x on the bottom. And that tells me right away that when the y value is 0, that's a problem. When the x value is 0, that's a problem. So I'm actually looking at all 4 90-degree values that are an issue. So at 0, 90, 180, 270, 360, all a problem. So I'm looking for this every 90 degrees is a problem. Every pi over 2 is a problem. So not starting at 90 degrees and doing a full rotation, not starting at 90 and doing full rotations. That's putting us right here and just going around, around, around. It's not just there. Again, it's not starting at 90 and doing just a 180 around. It's looking at not just every pi, 2 pi, 3 pi, 4 pi, 5 pi, and the negatives. It is looking at pi over 2 times n, 90 degrees, and just multiples of it. Every 90 degrees, multiples of it. 21, C. Number 22, use the following information to answer question 22. For a team photo, 9 volleyball players are to stand in a line. The photographer will place the shortest player at one of the 2 ends of the line and the tallest player into the middle. Permutations and combinations. So 9 volleyball players. 1, 2, 3, 4, 5, 6, 7, 8, 9. I go straight to the fundamental counting principle when we start looking at conditions and when person is at a certain spot. 9 positions. The photographer will place the shortest player at one of the 2 ends. So the shortest player might be here, or 1, 2, 3, 4, 5, 6, 7, 8, 9, or here. They're locked in. They're locked in. There's one choice in one of those 2 scenarios. But it looks like there's 2 scenarios. And then it says the tallest player is in the middle. T for tallest. One person has to go there. Locked in, no choice. So in either scenario, you've got a short person on an end, tall person in the middle, locked. And maybe there's another scenario where short person's on the other side, tallest person's still in the middle. But that means of the 9 people, there's 7 left over. So we have to do a descending 7, 6, 5, 4, 3, 2, 1, 7 factorial, times 1 ways to rearrange one of these scenarios where a short person's on an end. But you might have to add together this other option, 7 factorial, because that whole scenario could happen again if the short person's on the other end. So let's just take 7 factorial and double it. So let's jump into our calculator and do a 7 math over to probability. 7 factorial, enter. We'll double it, and we'll say these are all the ways that this scenario could happen. 10,080. Looking for an option, fingers crossed. 10,080 is option B. Feels good. Okay. Number 23. A circle is drawn with 6 points on its circumference, as shown in the diagram below. A student creates polygons with 3 or more sides by connecting the points with straight lines. These ones you have to read multiple times. the number of polygons that can be created that have at most, bolded, at most 4 sides. So there's 6 points here. A student creates polygons with 3 or more sides. So here is a polygon with 3 sides, triangle. How many triangles could we make? Or maybe the question is, here's a polygon with 3 or more sides. Here is a 1, 2, 3, 4, 5-sided shape. How many of those can you make? Well, this question is very limiting though, and it says how many polygons can be created that have at most 4 sides. So really we're saying 3 sides or 4 sides, but not 5 sides. We can't make a 2-sided polygon. We're restricted from a 5-sided polygon. So how many 3-sided polygons and 4-sided polygons can we make is the question. Ultimately, this is very much one of those combination questions where you've got a certain number of people or objects or points, and you're asking to connect like a handshake. How many handshakes can you make? You're asking to grab a certain number of those objects without consideration for order. These 3 points, if I rearrange the order that I drew that, it's going to make the same triangle. So this is a combination and not a permutation. So there are 6 points. We are selecting 3. There are 6 points. We are selecting 4. And the math for this one is a 6C3 plus a 6C4. So as we go to our calculator and crunch this in as quickly as we can, we'll say a 6 math 6C3 for the number of triangles that could be made. We're going to add to this, and I'll just throw in a bracket just to make sure, a 6 math over number 3, 6C4. How many 4-sided shapes can we create? And so there's 15 more, so a total should be 35 shapes can be drawn. And I do see option D is our 35, which again validates our thoughts. Okay, let's move on to number 24, nearing the end. The coefficient of the 9th term in the expansion of 3x minus 1 to the power of 10, written in descending powers of x, is. So I do know that when this is created, there's going to be some big number x to the 10, and then there's another x to the 9, and then there's an x to the 8, and this will eventually show up with a plus 1 at the very, very end, but there's a whole bunch more happening in here. The coefficient of the 9th term. Well, I do know that there is going to be 11 terms with that plus 1 at the end, but we're looking for that 9th term. So we do have, very conveniently, a formula which tells us how to deal with the expansion of a binomial. And this is the bottom here. Let me just zoom down here. This bottom, well, that's great. Grab that right there. Okay, so t k plus 1 is nck x to the power of n minus k and y to the k. So we're looking for the 9th term here, and the n represents that power on the initial expansion. K is going to be 1 less than the term that we are selecting. So I'm going to copy this down and try to clarify that a little bit. So we've got our t of k plus 1 is our nck, our first part of our binomial to the power of n minus k, and then our second part of our binomial to the power of k. So for this to say we want the 10th, we want the 9th term in the expansion, that means k would have to be an 8 for this to make sense. So for this, k is 8, and this up here, that 10, that is our n value of 10, and we're going to swap some things in here. So 10c8, our first part of our binomial is a 3x to the power of 10 minus 8. And our second part is a negative 1 to the power of k. That's our 8. And this is asking for the, again, 9th term. So when this is all tidied up, we have our 9th term. So let's go and figure out what is 10c8 without having to do a whole bunch of Pascal's triangle. What is a 10c8? 45. Okay, so we have a 45, a 3x to the power of 2. That's a 9x squared. And then a -1 as many times as we want should make with that even number a +1, so we won't have to worry about that. And so the coefficient on the 9th term, great. So we're looking for a 45 times a 9 as our final answer. So let's do a 45 multiplied by a 9, looking for 405 as a possible answer. 405, and I do see that as option D, which again sort of is validating. Okay, numerical response 8, our final numerical response question. Again, there's 28 multiple choice, 8 numerical response. Let's find out this last numerical response. 6 statements about the expansion of the binomial are shown below. The 2 statements above that are correct are numbered what and what. So we're looking for which statements, and it does look like there's 2 sort of parts to this. The expansion contains a certain number of terms. The largest exponent on the variable is something. So, when I think about a basic x plus 1 squared, and I expand that, x squared plus 2x plus 1, we just created 3 terms. It was a squared, but we're creating one more term than the power on our binomial, than the exponent. So why don't we just add 1 to our exponent and say we're good. So let's erase these. It was a power of n, add 1, and we should be good with statement 3. So we always have one more term than the exponent in our binomial. All right, let's move on to our statement 4, 5, 6. Which ones of these are going to be accurate? The largest exponent on the variable x is, well, how do we create the largest exponent? Well, I'm seeing an x squared and a 2x. There's going to be some balancing of the powers that occur here, but I know that every term is going to be created from some balance. Our very, very first term is going to have some coefficients, but there is going to be an x squared that has a power of n. And then the second part of this is a 1 over 2x that's negative to the power of 0. And then as every term is created, you're going to have your first term to the power 1 less. And then you're going to have your second part of your term have a 1. And essentially, you're going to have this descending of powers from the first portion, and the second part of your binomial is going to have this ascending order of powers. And so the greatest power that should occur here is the x squared being most impactful and being used the most. And so there is this x squared to the power of n that looks like it would be most impactful, and it would be the strongest with that x squared being used the most. So the largest exponent would be 2 times an n, which is our statement 4. So looking at 3, 4 as our choice for numerical response number 8. And the next section here is into the written response, and we'll do this one in a separate video.